this is I equals 1 to, call it n sub I. And we have a summation out here, j equals 1 to k for the number of groups that we have. And there's an equation. What changes is what's in here, how you measure distance. And this is not technically correct if you're a linear algebra person. See, I talk about all these math classes. If you're a linear algebra person, you'll know that needs a little mucking with to make it come out to be a number. But so where are the points supposed to be so that the sum of squared distances between the points and their mean is as small as possible? So in 2 dimensions, how are we going to do this? Let's do that. Sort of looks like the tobacco did. Where are those 4 clusters supposed to be so that the sum of distance between the points and the mean are as small as possible? We can look at this. Let's change it a little bit. Well, actually, I can leave it the way it is. And we can look at this, and the right answer is pretty clear. If we're going to make 4 groups, one of the groups is going to be like this, and one of the groups is going to be like this, and one of them is going to be like this, and one of them is going to be like that. And we're going to get some confusion about where that is. We can see that because it's 2 dimensions. But we don't have 2 dimensions. In the tobacco data, we have 27 dimensions. We can't see that, even though we know that this is what's going on. In 27 dimensions, we can't see it. So how are we going to solve this problem? How are we going to find the right minimum of this? Well, there's no calculus to be had, because the number of groups, you would want to figure out the number of groups would be a variable in your, it doesn't, no calculus. No calculus means that we need an algorithm. We need a method for solving this. I can't do a grid search because it's way, way, way too hard. So I need some other method for solving this problem, some other algorithm. There are hundreds? I don't know if hundreds. Lots and lots of algorithms have been proposed for k-means. The one that most software, so okay, now we need to understand what SAS calls FAST+, and I guess I'll just talk about the SAS one. And I know SPSS has the same type of algorithm. Basically, you get to tell the software what algorithm to use. This is rare. Usually the algorithm is chosen by people smarter than us. But that's not the case in k-means. So what's the FAST+ algorithm? Can't be a grid search, that's too hard. It says pick the 4 means as, and I think I mentioned this, as the 4 points furthest furthest from the multivariate mean. That's what it's going to do. It doesn't, the reason that it does it is these points are fixed. They're easy for the algorithm to find. There are 4 defined points based on the data. Multivariate mean, there's some more points up there, might be right here in our 2-dimensional case. Which are the 4 points that are furthest away is an easy, simple calculation. Doesn't matter how many dimensions you have. It's super simple for the software to find those 4 points. And in this case, it might be that one, that one, that one, and that one's pretty far away. So just for fun, we'll make it that one. Question?
Is this always going to be Euclidean distance, or is there going to be some sort of...
It depends. It depends on the algorithm. Typically it's Euclidean distance. But then sometimes you notice in the software you can standardize the variables. So if you standardize the variables, it's using something called Mahalanobis distance, which is, some software packages will give you a choice between Euclidean, Mahalanobis, and something called Manhattan distance. All of which are different distance measures. And then they give you an answer, an option of whether you want to standardize the data. In general, just remember that standardizing the data lets all the variables be on the same sort of playing field as far as importance goes. And it's not necessarily a good idea to standardize the data. Oftentimes it is, though. Especially when things, you got something that's measured in miles per gallon and another variable that's measured in RPMs. It's like, well, what the heck are you supposed to do to make it, which variable is the most important? You don't want it to be the one that is just the biggest. And so standardizing often makes sense. Then, step 2, so that's this generates what are called the starting values for the 4 clusters. 2 is assign all the points to the nearest call it a center. Three. Recompute the cluster means. So what it's going to do is it's going to say which among the 4 choices, every point is closest to one of the 4 means that I've got so far. And obviously these points are closest to this one. These points, it's like, oh boy, I don't know, are closest to that one. That guy's a little closer to that one. And that guy's not closest to anybody. So he gets stuck with one, and then we got to assign all these guys up here. Oh boy. Maybe they're going to join this one. Four. You're done. This is why it's called FastClus. It's incredibly fast. It doesn't always get the wrong answer, but in real problems, I don't think I've ever seen it get the right answer. Get anything remotely resembling the right answer. In fake problems, it can get the right answer. So if this was sort of real looking data, and in fake problems, our clusters might look like this. If I simulate data, I can simulate 4 clusters that are separated by a certain amount and go, oh, look, the answer is obvious that there are 4 clusters. And if I feed this into FastClus, it's going to say the mean is here, multivariate mean is here, the points that are furthest away are here. And life is good, because then all the points get assigned to their nearest cluster, and this cluster is like this. And a miracle occurred, and FastClus got the right answer.